Okay, I'm going to also start with the most famous quotation from Jacobs, and then in this program, and then the best pattern recognition system is still in the human brain. I may just want to push it a little bit further. It's like actually in the human intelligence, we can go beyond the pattern recognition. And then now let's look at these few examples. And then so all these few examples we can recognize, and all these like letters, and from the different images we can recognize objects, and then we can recognize actions, and all this kind of like recognition, and then we can get and from the image patterns. So I used and then this very simple and formula and in my first talk, and then to kind of try to and use this Bayesian and then framework, and to understand and then how humans can update their belief and then in light of the data. So if like for pattern recognition, and then in the sense is that we actually have a good knowledge about hypothesis space. That's what our domain knowledge really can help us. And then we have knowledge about what this letter looks like, and then we can create some good likelihood function, and then we can update and the belief and in light of the data. So we can do that, and then the intelligent system also can do that. And then now, but if we move forward and to look at, we do have some situations. It's very special, and then for human system. So for example, and then these are the examples, and I like to put down here. So the first one is actually it's the real and then bronze and the sculpture, and then which called the Travelers, and then this is actually made by a French artist. And then you notice that, and then what we see here, we have no trouble. There is a big chunk and missing in this sculpture, but we have no trouble and recognizing and then this entity. And meanwhile, we also appreciate and the aesthetics and the art parts and then from these types of display. And then this actually is from Picasso, and then just a very simple few lines, and then you kind of can perceive under the camel and so on. So these types of example to me, it just showed not only and we have this kind of domain knowledge and we have this idea about hypothesis space, and our likelihood function is incredibly robust. And even though we don't see and these types of patterns and in our typical and learning situations, but we actually can generalize and to these kind of new types of display. And then the other types of things I also find is extremely interesting, kind of what I call this will be beyond the pattern recognition. So these are the few examples. So the first one is related to social perception. When we see this image, clearly we can see under the expression, facial expression and from this baby, and then but we can see something kind of like he seems like very determined and to do something. We see that determination here. And but actually, what happened is that this is the expression after first taste of sand. But it's interesting. It's like it's really we see something on the beyond it. And then this is another example I like a lot. And then we see, okay, we can recognize this is a rabbit and this is the hen, but we somehow see humor out of it, right? So because like this rabbit made this like a very unusual posture, and then you can generate this hand shadow. So we see humor about it. And the last one I put down here, if you have ever done the intelligence test, and then you did this problem, and then this is called the Raven's progressive matrix, and then what you do here is that you are trying to figure out the relationships, and then across the different patches, and then you are going to apply this relationship, try to fill in this missing patch. So now this you can think about it, all these types of the problems. We still tend to say, use this phrase and in human language, which I like a lot because of the vagueness I see. And then I can see these patterns and then in these images. And then furthermore, and I see from the left to right, start more closer to understanding here. There's no specific like pixel, and then in this image, pointed to humor, pointed to like beauty, but somehow you can see and then these types of higher order related to higher cognitive attributes and come out from these images. So, and then Jacob also talked about the tasks, the importance of the tasks. I want to, in today's talk, mainly kind of like inspired by this task because we widely use to measure intelligence. So using these types of Rivens and the progressive matrix problem, and then so we can has been widely used in psychology and to measure and the fluid intelligence and in humans, and then recently and also the AI system and trying to do use the similar test to do it. So I basically can tell you, and then when you get into an intelligence test, and you will get the instruction, which is and there are exactly I will read the instruction. There are 8 patterns, and in this 3x3 matrix, and the missing one and must be determined and from these 8 choices, and there is a rule, and then to show you and how the pattern change and from the left to right, from the top to bottom, and then you just apply the rule and then to figure out the answer here. So now this is the question here. So for this particular example, what's the answer you will get? D. Yeah, this is actually the number 1, the easiest. And then in the Rivens progressive matrix, it will become harder and harder. But you notice that and why it's so important. And because from from psychology perspective, and there are a variety of the tasks and showing in this diagram. So the green and usually and related to tasks and relevant to language, to semantic understanding. And the yellow are a bunch of the tasks and related to perception, related to spatial cognition. And then the blue part and related to mathematics skills and so on. And all these different tasks, the people's performance, and at the center, they all correlate and with the performance in Rivens progressive matrix. So that's kind of like why we call it the intelligence test, because it's a very good metric and then to differentiate individual differences and then for these types of reasoning problems. So, but like this is the most famous task and then for measuring the human intelligence. But commonly, and then this task, and then you can put it into a group of task set and related to analogical reasoning in psychology, and then we actually have a variety of the stimulus, and then we can measure the people's ability doing analogy. We can use this kind of visual displays, and then we can use just these simple geometric shapes and new relations, or we can use something, and we have some kind of domain knowledge, and then even can extend it and then to these images and related to the social relations and so on. We also have a bunch of like task banks and then just use the narratives, use the words, and then just based upon your semantic understanding and so on. So now you can see there's a variety of the tasks and the stimulus we can use and to measure these types of the reasoning ability. Now, when people are trying to study and then these types of analogical reasoning and the capacity, and in the past there tend to have 2 approaches and in the literature. So in the past 4 decades, the emphasis and would be like, okay, I gave some kind of like a source domain. So in this particular example, it's an analogy between the solar system and the atom system. So this is a very famous, and then this is a very famous analogy. And then when you're trying to understand the atom system, and now you can use the solar system, and then to figure out the entities and the relations, you are trying to align the representations across very different domains. That will help you to understand unfamiliar domain. For example, you don't have too much knowledge about the atom, but if you know something about the solar system, and you can transfer this knowledge from a familiar domain to help you to understand unfamiliar domain. And so in this case, and then this is actually the diagram and developed by researchers, and then try to capture the relationship between the different entities, how these entities relate to each other, so you can get these kind of graphs. And then now, in the target domain and the atom system, you generated a similar graph, and then you are trying to do this representation alignment. So then, in the past 8 years, and then there's a different approach and emerge for doing this kind of analogical reasoning and do these types of tasks, is to use this end-to-end and deep learning. So the basic idea here, and started from this Rivens progressive matrix task, and then you actually can supervise and then the neural network models, and to give them like a massive amount of like analogy problems. And then at the end, and then they will emerge and to show ability and to be able to solve these types of the problem. So this actually is shown at the performance level. It's impressive. Because then, for example, if I look at how well the people can solve these types of the Riven's progressive matrix problem, and then you can see that then by 16 years old, then their accuracy can reach about 82%. And then these types of the relation network can train for these types of the problem, and then can reach something similar, 75%. But here, there are a few red flags. And then, so for the first red flags is that in order to reach this performance, the network need a massive amount of the training data. So when I just showed you this problem to you the first time, all you have is just the instruction. So actually, when humans then they do these types of tests, especially for kids, and the parents are instructed, do not give them any practice. And then they're supposed to solve this problem on the fly. And then when they look at this matrix, they need to figure out the rules and apply these rules to the new situation. So the training data to humans are very, very limited. And then, but these types of deep learning types of the models, usually trained with hundreds of thousands of the problem similar to this. So this is a kind of a learning from the big data, and then so to solve this problem, and then the data set had to create and then about 1.5 million problems like this, and using the different shapes and using the different relations, so you can create this very large data set to train this model, and then the training comes from 300,000 problems. The other things and then also highlights here is that sometimes they show a very weird generalization performance. So for example, and then it seems like, for example, if you learn particular rules, like earlier, and then Erica talking about these successor rules, and then in numerical and cognition, and then if you just show this successor rules and using color, and then just the redness will increase and during the training, then you apply this one to the number of objects. You apply it to the size of the shape. And then suddenly this rule cannot be applied to this new feature dimension, even though this feature dimension had been learned with other rules. So the kind of the idea here is this combination of the attributes and the relations need to be interpolated within the training domain. But and then when you get into this extrapolation regime, and then they cannot combine them together. So that's very different from how human would solve this problem. The other things, and I think is also very representative from psychology, is that why and then this analogy ability really represents and is a prime example of human intelligence. So this is actually my favorite study from Dedrick Gardner back to 1977. And she actually asked the question to preschoolers, if a tree had a knee, where would it be? So the preschoolers, they actually can correctly and consistently, systematically, point to the right spot in the tree. So this is the kind of, no one just teach them. And then where is the knee of the tree, but they would be able to generalize their spatial knowledge to the novel domain. So that's kind of part of the reason I think it really reflects the creative part of human cognition.
I'm sorry, what's the right answer?
The right answer is here. And adults also do the same thing. And another cool, and
is
then
that right, or is that the right spot? It's just that because we have no diversity, that everybody, we have complete consensus of imagination.
it's very systematic, it's very consistent. And then adults and the kids, and then they basically put down here. And then they also, in the experiment, they make the tree kind of upside down, and then they make the tree and it's lie down horizontally. They put it on the right spot about the trunk here. Yeah, that's actually quite amazing.
Where trees walk, right?
Yeah, but it's still, I mean, I feel like
Yeah,
right. It's
yeah, that's right. So not only they use the trees, they also use the mountains, and so kind of where is the head of the mountain and so on. So that's kind of like the generalization of this spatial knowledge. I think I have another question. Okay. So now let's look at the next step, and then so for example, if a human can do that, and when we 5 years old and 6 years old. And we really can generalize the knowledge and to an unfamiliar domain and to get these creative answers here. And then they also can ask the question, if the tree had a face, what that would be. And then, so the young kids and actually also gave like very consistent answers and then get to the top of the tree and so on. So, yeah.
Has this been given to machines to see what they do?
I think and then because and then this example now becomes so famous, and then when I do that, the ChatGPT actually got the right answer. But the question is that we don't know is that they have seen and then this example before, and or they really did a generalization. But I will show some types of examples and at the end. Yeah. Yeah.
Just ask GPT-4o and it says, then you would be in the trunk.
Yes, yeah. And then we also tried that, and then they actually can solve this problem. Yeah. But I think some of this analogy problem is so famous, and then because
it's training data.
Yeah, I think the training data, because in 2022 we tried a bunch of them, some of them they cannot solve, but now 2024 we solve most of it.
There's so many fairy tales about trees being human-like and walking and all of this, so it's kind of, I'm sure that's tainted by this.
You mean like for ChatGPT or for the 5 years old? And for adult, that's the good. That's like kind of like good thinking here. I think for adults and then probably, but like for 4 or 5 years old, I'm not 100% sure. But on the other hand, I think and then it's not like someone specifically tell them, and then the knee of the tree would be here. It's actually the kids and make this inference on the spot. So that I think that's like an interesting part. Yeah. So now, and then I want to show the first example, and then it's a very simple exercise from our end. Is really, and then to compare, and then these two types of the approaches. So one thing, and we have been doing is that, so in Riven's progressive matrix, and then you can use the shapes, and then put them different relations, you can generate many questions here. So what here we are trying to do, okay, how about we introduce and some prior knowledge and to human, but meanwhile we also can generate many different these types of analogy problem. So we use a very simple and then scenario, basically it's a part-whole relation. So you can think about it here, and we can use different like 3D models, like the car, and then this is the whole car, and then this is a part of the car. So we can say, okay, now what's the relationship? Human participant will say and figure out what's the relationship between this left image and the right image, and then apply the same relationship, and then to figure out what is this missing piece here. So there are some kind of very interesting for us, and then we can do a lot of like experimental manipulations, even though it's a part whole, but it does require and then this precise relationship between this piece of the image patch and with the whole image patch, with this whole image patch here. So we can create the situations like that. So similar parts and from the different object, or just like from the different parts of this object. The other kind of very interesting thing, and you will use your domain knowledge, we can create the situations, this is the correct answer, is that the part actually is not showing in this image. And then so that will require you to use some of your knowledge, previous knowledge, and then to repeat, to complete, and what's the parts and the behind and this car, and then to generalize this knowledge and to the new situations. So this is kind of the situations we can create and many different experimental conditions we can measure and the people's and the behavior and in these types of the analogy task. So this is the different kind of experimental conditions we can create. And also another nice thing here is that we can use many different car models here. And then we can create the different pieces, and then we can create a very large number of problems so that we can train the deep learning model. So what we did here is that we can create the 30,000 analogy problems by using the different car models and put different texture and different background here and to train this model. So here, and what we're going to do is that we just gave like many different, like 30,000 and 20 examples and to the relation network. And then this is a supervised training. So every problem, and then did you solve this? Did you solve this problem correctly, or you solve the problem wrong? And the errors, and we'll trace back, and then try to update, and then the weight, and for this relation network. So now, if we just do the experiment, we compare and with human performance, it's actually not too bad. If I look at and then this analogy task, and then this is the harder task for human, it's not easy. And so you can get the human will get about like a 60% accuracy, and the relation network can also get something close. And then clearly above chance performance. So at the beginning, we were very impressed. It seems like, okay, and then you don't need all this kind of knowledge. It seems it can be learned, and from this 30,000 and then problems, you give them enough problems, it seems like they can do this task. But then what we did is one control experiment. So in the test, what we did and then gave this model is that we cover and this whole image. And then so now we say, okay, make the choice. For humans, and then the performance will be chance level because we don't know what exactly the relation between that. And then the relation network, it's the same performance. And then what I mean, it's like, I think on its own, it's impressive because it's learned some very specific strategy for solving this problem because we created this stimuli. And they find the strategy is that they can find some visually most similar parts, image, but not identical. And through the training, and then from this 30,000 problems, and then with many, many parameters, and then what they learned is to learn this very specific strategy and to be successful for this task here. So this actually led to my yesterday's talk is that now you have a system, everything is modeled together. How you represent this object, how you reason about this object, it seems like all together and then within this network. And then you're not taking this functionalism and the types of the ideas to decompose and the different components based on their functions. So we just did a very simple experiment or model. And then so what we did is that we just separate and then your vision module and then your reasoning module here. So for the vision module, and then we can just like use and some computer vision systems and to get the representation and for each of these images. So what we did here, it's pretty straightforward. We use the standard and the convolution neural network model. We use some part segmentation model from computer vision. Each of the image and will be represented as an embedding and in this high dimensional space. But they have some actual information in this embedding. It's know what are the parts, and then they also know, and then the appearance information, and then geometric information, and so on. So all this kind of information will be encoded in this high dimensional space. And so you can think about this image, and it will be and transform and into and then this vector in the high dimensional space. Now the reasoning becomes pretty simple. So we can look at the difference and between these vectors and for these two image patches, and then compare it and then to the target, we can find the answer to it. So this is a very, very simple and strategy, and then but we just separate and the visual representation and for the images, and then now just do the comparison and for the reasoning module, simple and then simple modeling and strategy. So now in this case, and then the green here and indicates the human performance across the different conditions. And then the other bars, and then the first two bars, and indicates two different neural network models, and then they use different architecture, and they don't capture the human performance very well across the different conditions. This very simple and model, and by separating and then your visual perception and the reasoning module actually can capture and the basic and the human performance. Yeah.
I think I'm still a few slides behind. How do you, when you have covered part of the question, how do you know there's only one answer? Like, how do you know which is the right answer if there's nothing to have a comparison to?
Right. So what's the deep learning model we gave to it? So this is just become a gray image, and so you still have the same input, but then they will be forced that you still have to make the choice among these four. So they make the same choice.
Oh.
So that kind of a reason is like all this training and through this complicated network and what they learn It's you can summarize and using this strategy. Yeah.
Something's bugging me. I think on this one, the answer should be B and not D, right? Not that one. The one, nope.
No, the definitely not D.
No, it's B. I think is the best one.
This one, yes. This one is B.
Right, but
Yeah.
the other one was marked correct or something on it. Never.
It's D, because
D
B is the same kind of car as the green car.
Right. No, this
I
one,
see,
no,
I see.
not D. So you have to
See,
be
the
something.
position of the
apart
wheel
from
is
the
better
bottom.
at B.
Yeah.
Yeah.
What confused me about this one is how do we, as the person setting up the experiment, know the
All right.
first image is still a green
Yeah.
car?
Yeah, humans, you can see, and put the human not do the perform because we cannot make the choice here. And then so.
Or make the final answer, you know, like how do like what if I wasn't thinking of the black car anymore and I was thinking of a different car? I don't know. Or a gray car that wasn't a gray car where the answer would have been B or something like that.
Right. So that's kind of like the interesting part here is that what if you gave this one to the humans, we're likely just go for the D because we just choose whatever is similar here. But the network learned is that I find the visually similar but not identical because this one and this one they're identical. And because in the training data, it's actually learned and not to get to this foil here.
How does a researcher know that the answer is not B, for example?
The ground truth, I think.
Yeah, the ground truth and for us. And then because the ground truth is defined by this problem.
Yeah.
And then the problem is that if you cover these whole cars, this keep the same answer.
So you decide first. There's no
Yeah.
like chance of saying, "Oh, I changed my mind. It's going to be different." You know, like tricking the machine or something like that.
Right. So in this particular case, because we get the patch and then from this image and from these 3D models, we know what is the correct answer. Yeah.
Why did you cover both of the whole cars and not just the first one?
If I cover this, and then so for that's actually kind of like an interesting question here. When we just do and then when we did this kind of a model simulation, we just say, okay, we just cover the whole cars and for both and then this source and then the target here, just to make them matched. Otherwise, and then you kind of like you have this unmatchedness and between and then the source problem and the target problem. Yeah, but I think and then your question would be like, okay, if I show and then this is if I show it, I can test it with the model, not the human. I can cover this and then model I can show and then still this car. I would think the model performance will still be the same because it will apply the same strategy. So what this kind of showing is that even though what we want for humans, it's very naturally we figure out what's the relationship and between and then these two images. But for model, it's not what they learned. It did not learn and to capture the relationship between these two images.
How do you know where the noise is coming from, whether it's coming from the visual module or the reasoning module?
For the relation network, we don't know because they're all lumped together. And then so that's part of the reason it's lead to my later talk is that for these types of the network or architecture, it's very hard for us to encode and where and they learned under the relation. In this particular case, and this simple example, they actually did not learn the part-whole relation and between these two images. They just find a shortcut, a strategy, and for that particular training situation. Oh, Mark?
So, in a lot of these, I feel that in my attempts to solve them, I'm using language. Certainly in the Raven matrix. I don't know those of you who solved it. I mean, but I can't imagine solving that as easily if I didn't have language, which of course encodes a huge amount of knowledge. And with this, I mean, when you showed the back of the car, my mind is saying, this is the back of the car. That's not saying, well, it's not purely visual. And I wondered to what extent you have methods that prevent language from being used. You can test whether humans are doing these things without using language by having a problem set that language would not be helpful for.
Right, and I think our next task, and then actually we have some kind of ideas about that, and then try to, I don't think the language is very easy and then to be directly used to do a real like a core and a visual analogy problem. And also for the visual analogy problem, what I showed the Riven's progressive matrix types of problem, you can translate using language. But then they also use the other types of like simpler relation purely based upon the visual, kind of visual features. That has been tested with animals and so on. So that part, and then they don't have the language system, but they actually still can do under the task for some simple relations. Yeah. Jacob?
So I'm curious if you did the experiment where you gave the masked thing to humans.
Like this one?
Presumably they would eventually learn this heuristic.
You mean like this one?
Yeah.
Human.
Yeah, and I'm curious whether the sort of performance curve would look more like a kind of thing where there was some insight learning as opposed to, I assume what happens if you like looked at the relation network performance at various stages over training, it would just get progressively better, whereas humans would probably at some point say like, oh, I should find the car thing that looks the most like this but is not identical.
Right.
Now I know how to do it, and so you get like a very different performance curve. Have you thought about doing that comparison?
Yeah, I think it's a very interesting idea. For this particular case, this strategy is very odd for human to use, right? So it's almost like we're trying to learn a concept and using and then some specific kind of logical form, and they kind of very unnatural concept. I think if we gave enough like reward, and then I think people will learn, and then this actually is the rule and the strategy you are using. It will take time, but I don't think it could be like have an insight and show up and in that particular. But this is not the strategy we naturally come in. And then we naturally come in, it's like, okay, this is a part-whole relation. I'm trying to figure out how this part and it relates to that whole. Yeah.
Now that Jacob's raised the question, I realize something I didn't understand about the experiment. So when humans are doing this task, do they find out at each step whether they were right or not?
No, we did not give them feedback.
So, because, I mean, it seems to me humans could do this without whole car image thing if they were finding out what was right and wrong. I mean, it seems...
Right. So in this case, and then what we focus here, that's also another interesting thing, is that we focus on inference in this particular situation, how you solve this problem, and not learning. If we just like give and then some reward function and correspond to this particular strategy, I think giving and the specific and like sufficient amount of the kind of training examples, humans are able to learn. But the analogy, the special part is that it's really, and then there's no learning. This is kind of like in machine learning will be one-shot situation. I have one example, and then in this case, and then you are trying to solve this problem. That's the extreme situation. Sorry, I think I now have a question in the back.
I think in the back, okay. No, I'm just wondering because the human brings with them some preconditioned learning already, and we don't know what they are bringing with them, as opposed to the machine where you are giving the data and you know exactly what is doing.
Yes.
I wonder about the aspect of unlearning some specific things, not just the learning for the humans. And I guess one of the benefits of dealing with humans is that you could ask some questions so that you can get some insight about why they made those choices. So it might be something you can do.
Yes, yeah, and the kind of a learning is another kind of very important aspect for us. So in this particular experiment, and we did not touch on learning because we have all this domain knowledge, we have this relation, it's already built in and in our knowledge system. So we just use that and to do the inference here. But the learning is a very important aspect here. But the one interesting thing about these types of the problem analogy, it really gets into this kind of, I make an inference and with a very small number of demonstration. But I also backed up with a lot of domain knowledge here. Okay, I think I have a lot of questions. And then with the time constraint, I think I will move on and then hold your question and then we can discuss and after this first study. Okay. Okay, so this is a kind of like one thing, it's a simple and illustration. But now the next thing I want to do is that I want to show if you take this functionalism and the perspective very seriously, and then so now and when you build up the modeling system, you want to decompose and then this complex capacity and into and then the less and the complex capacity in this case. But like we also want to look at what kind of computation people could do. So in the previous example, and it's still simple analogy problem, and then we are just looking at the cars, and then the parts of the cars, and the specific relation, and the part-whole relation. This is what I think is the harder analogy problem. And then so now in this case, and then I illustrate, and this is a cat. I have the few dots, and then here to indicate here. Now I have the horse. It's very different and the object categories. I will ask you, and then which of the dots and in the horse and can match to and the dot and in the cat here. So this is what like we call the far analogy. Of course, here I'm using language and then to give the label and then to help you to understand what's going on with the task. But in the experiment, we don't give this kind of language label to human participants. So can we just do these types of through the inference and then to make this kind of a mapping task here? So in this work, and what we have been doing is really to increase the computations and for representing these images. And then we also kind of can increase the computations and for reasoning to do the matching here. So the basic idea here is that now the image and then for this each of these points, and then we can represent it as this kind of a relational structure. And then so we can use a graph and to represent it, and then each of these nodes can represent the image patch surrounding this point. And so this can capture the appearance and the geometry and so on. And then for this particular local patch. And then the edges, and we also can use the embedding and to capture the spatial relationship and between and different points and how they relevant and how their relations and to the other. So we can use this attributed graph to represent and then the appearance and for the local context and the relationship and between the different points here. So we can get it for the cat image, we can get it for the horse image if we give these points here. Now the next thing that you could do is that basically you're doing the graph matching here. So now for the graph matching, and then in this case, we can just use and then the standard, the Bayesian and the formula to the framework. And so I have two graphs, two attributed graphs. I'm trying to find what's the matching here. I can decompose it into the likelihood function and the prior here. So the likelihood function in this case and is actually the similarity. We're trying to make and then the match and then the points, the nodes, and then they're similar to each other. So it's almost like a visual similarity here. But we also have the relation similarity. If and then this left, if this point and then to this point, they have certain relations. We want and then this relation also is mapped and then to the matched points and in the different entity. So we can use, you can think about this similarity is driven by both and the visual features and the relations and between these visual entities.
What if one has more features, like the horse has a mane, which the cat doesn't have, right? So wouldn't the graph have an extra node?
Yes, it will have the extra nodes, but you can deal with that and by adding and then you allow and the nodes are not matched and so on. So you can create and this kind of a mapping matrix and then you can have a column and get like basically a slack there. Yeah. And the prior here, it's pretty simple. It's very generic. And then you will favor and this isomorphic mapping. You want to, best scenario, one-to-one mapping. But because you add it to be a probability, so you actually have the flexibility here. So sometimes and then you don't have to exactly end up one-to-one mapping, but this is some of the situations, the states you will favor to. Then you can incorporate and then these constraints, and the likelihood comes from the similarity, and from the visual patches, visual appearance, and the relations and between the different parts, and the priors and more favor and this one-to-one mapping. And then you can do this kind of like a task here. I can give the two images here, and then people and can figure out which point map to which point. You can do a deep learning types of models by training and with I think it's like about 200,000 examples, giving a correct mapping here, and then try to learn and to do this task. And then, or you do this one-shot learning situation. Directly do it as inference. Your performance is better. Using the system, and then you actually, in a deep learning model, it's always trained and doing this near analogy. So kind of means, and then the entities and from the same object category. But now, if you just treat it as an inference problem, you actually can do it between the category mapping here. So you can map and then the cat part and do the dog part and so on. So this is a kind of like a very interesting and modeling project for us, because now and then what you can see here is that you don't really need a language, and then but you rely on your knowledge about this object, and you rely the knowledge and then from these patterns and in this local context here. But the other interesting thing I find is more fun is to look at where and then this model would fail. So this actually is an example here. So green is indicated as the right mapping, and then the red indicated the wrong mapping. So what happens here? And then we find this actually number one types of errors this model would make. So basically the left and the right, the model did not have a right idea about the left and the right, because it did not have the 3D model of this object here. So the next thing what we did is that can we extend the same framework and to the 3D objects. So now in this case, we're looking into like 3D objects. And then the input is not like image patches. The input and will become, and then the point cloud, and to capture, and then this geometric structure of 3D shapes. So now in this case, you notice that, and in this kind of in the model, and in this model's black box, it's still the same thing. And then we can form and this structured and the visual representations. But now, and then you have all these, each of these points in this case, you have like this 1,000 of the points, you can get the parts, and each of the parts, and then it will be represented as the node embeddings, and then you get this geometric relationship, you get the edge embeddings. So even though the input is the sample, the 3D and the point cloud, but and then the internal and the computation still remain the same. And then you can try to figure out and then what is the relationship, and then what map to what. Now you can do this kind of the generalization, and then with using the same type, using the entities, 3D objects within the same category but different styles, or you can do and then these types of mapping and across object categories. So this actually what I'm going to show you is some kind of animations, but this actually kind of showed you and the basic the snapshot about it. So you have all these points, and for a chair, if they have the same color, that means this point, the head of the point, correspond to the head of the dog, and the leg of the point and correspond to the leg of the dogs. And this is what the model and can discover and these types of the relationship and the mapping here. So now in this case, and for example, chairs, and they could take a very different styles, but then your basic mapping and still maintain it's similar. And then the horse and the dog and the similar situation. And the interesting part is that you actually can do this kind of like a cross an object category mapping in this particular case. So we can get this model performance, and then for these 3D objects, we also can do a human experiment. So for example, in the human experiment, we can show under this 3D object, we put the dot and then in one object, we ask human subjects and then to move the same color dot and to the map, to the matching part, and for the object showing on the right here. So this is just like a recording of one subject doing the experiment here. So we can measure, and then we can have a measure of the human performance, and for different conditions, like we use animals or chairs, within category, cross category, and then what's you showing here, the violin plots, and it indicates the human performance, and then the other ones, and then the dots here, and indicate and the model performance. It's actually capture human performance and pretty well. But now when you have and then these types of computational model, you actually can really apply it to very different domains. So we also apply it to narratives. So rather than the visual input, and then you can give subjects and then kind of like this kind of narratives and using language here. So this actually is the most common and then stimulus people have been using and in psychology to study and then analogical reasoning. So you can think about you have a narrative and to describe the solar system as your source. You have a narrative and to describe an atom system. And then you can use some of the language models to get the keywords and then from this narrative. And then you can use this narrative and then you can use like word embeddings and for these keywords. And then you can use a different model to capture the semantic relations and between each of these two keywords. And you can create and then these types of attributed graph. We call it a semantic relation network. And then you can do the mapping. Then you will notice that and after and then this mapping, what you can get this very nice correspondence, like the sun, it corresponds to the nucleus, and then the planet and correspond to the electron, and so on. Then you can see these types of correspondences. So you could, another way, and you also can further apply it to one of the most famous analogy problem in psychology, is that there is a story, and this is applied to problem solving. So for example, and then you ask people to solve a problem, you have some kind of like, this is represent a medical problem, it's a radiation problem. And then so basically, and the doctor is trying to and then design the system to kill a tumor. And then there is a different constraints. You cannot use the laser too strong because you could kill. And then the other types of healthy tissues. And then trying to solve this specific problem here. And then if you directly give the problem and then to a human participant, they actually have trouble solving it. They cannot figure out a good solution for this problem. But then you give them a story. This story, how this general and then make a strategy to conquer a city. So the general is doing it actually and divide and the soldiers into different teams. And so they have this convergence strategy. And so they can win and then this war and then they can conquer and then this city. So on the surface, they are very, very different domain. But after giving this source and this general story, and then more people would be able to transfer and this convergence strategy and into this radiation problem to solve the problem. So we can use exactly the same paradigm and then try to find the mapping here, and then you can help you and then to solve this problem. Yeah.
So for the graphs for each narrative, how are the edges formed between each word?
The edge?
Yeah.
Yes. So the edge and then here, and we actually have a relation vector. So in the relation vector from a relation model, it's actually also through the learning here. After the learning, and then we actually have a predefined set of the semantic relations. So it's about like 200 semantic relations and defined in linguistics. And then now, and then what we can do is that we can give any of the two words and into that model, they will spell out the relation vector, and each of the elements indicate what's the probability. These two words indicate antonym. What's the probability, and then these two words, and then represent the relation, kind of, and so on. So, and then we can get, and then this edge, the attributes for the edge there. So that's kind of how we capture the relations. In the vision domain, under the edge, and more focused on the spatial relations and so on. Yeah, you're welcome. Okay, so what I've been showing you here is that if you first, and then if you want to capture and then this inference problem, you want to separate and then visual representation and or semantic representation, and then you can use a reasoning module and to do these types of mapping. And so that's actually lead to, and in your representation, it's important and to explicitly represent the relationships. And then so here, and then we actually studied a bunch of the relations and like part-whole relations, spatial relations, semantic relations, and so on. But this is not all the relations and we use when we do the inference here. We have some other relations that we tend to use is what I tend to call them is the generative types of the relations. So kind of agentic relations or causal relations. If you have a way and to capture and these types of relations, put it into your model, and then that actually can dramatically increase the model's performance. So here I want to quickly just show one example. Actually, I call it the agentic relation. I'll show you a one of the most famous animation and in psychology. So you can look at the movement of these shapes. So usually when I show this animation, it's like after a half minute, people started to laugh. The reason you started to laugh is that you start to see and then these types of social relations, and just from this simple movement of these geometric shapes. This is not anything and we see and in daily life, but somehow when we get into this representation or this kind of display, by looking at how they move with each other, you figure out who's the bully, and then who's trying to help the other one, and then who's trying to hinder the other one, and so on. These types of the agentic relations come out and then from just simply from the trajectories of these shapes. So here, and then what can create this kind of agentic relations, if you think about it, and the one possibility, if you are moving the objects, you're throwing objects, these are the physical forces, and then you impose this object. If you are an active agent, and then you have the self and then generated forces, and then to help you to move to the goal and towards the goal and so on. So this is what we call the social forces. If you have a good understanding or capturing of these social forces, and then you actually can capture these types of relations, because the relation, the relative movement between the entities is governed by these types of the force function. So we have another kind of like a project, and then we have been doing is that we can create this kind of to train these physical models, to train the social models. We don't need too many videos, and this about like 100 of videos. And then we can figure out from this training this social model, we can figure out what are the variables are important. And then what is this kind of a physical equation, and then you can capture the forces in this physical environment. And then for these types of the social model, and then you will outcome, the outputs, and then will be, and then this type of social forces will help you to figure out what are the variables you need to put into this social force equation, and then also these social forces, and it depends upon your goal stage. So that's actually indicated and then in this graph. So all these things, and you can learn it, and just from about like 100 videos here. But the part of the reason is that, and then these types of the functions and the variables can be identified, and then directly to capture this agentic relation. So, for example, and then in this particular case, and just showcase what you learned from this simple model. This is the particular video is that this red dot is trying to leave the room, and basically the red dot has a goal position. It's indicated by the door here, and then this green agent is trying to block it. So now you can see, and then you learn that the values is quite different. So now this is actually the values or the corresponding on the force field, and then for this green dot. So you can see that if the green dot is here, for the red dot who's trying to leave the room, it's clearly, and you have a high value and around and then this door position. You basically, all you are trying to do is just move from any of these locations, move towards this door location. But now for your green agent, you are trying to block and the red agent, then it will be like the green agent behavior will depend upon where and then this red dot would be. In this particular illustration, for example, the red dot is here. So now what happens is that the best value, best location the green dot should be, it should be here, and then not exactly at the door, but close to the door. And then if the green dot is here, then the green dot and need to give himself a very large force and try to run towards this location. If the green dot is here, and does not move too much here. So now these types of the social force and will become, and you can capture and then how you give yourself and the self-propelled force and in order to get into a goal location. So if you based upon the different location, you can see and then your force field and then for these green dots and it will change. It depends upon the location of the red dot. So if you can capture this kind of physical force and the social force, and then you can make a prediction to 100 of the videos, and we have been showing to human subjects, ask them to make the prediction. Is this a human-human interaction, human-object interaction, or object-object interaction? And you notice that it can perform much better and to correlate and with human performance, and then direct the deep learning model and trained and for these types of the videos. So I think another interesting part, and then in this case, and it's really just to show that if and then in your model and to capture and then human and behavior, it's really important and to explicitly represent the relations, and then you can create generative models and to capture the relations and between and the different entities. So because part of the reason why I also think that relation is beyond the simple pattern recognition is that it's not, there's no pixel and in the image saying, okay, I'm above. It's not something like that. And it's more like the mental structure, and so that you can represent and then these two entities in a coherent way. So earlier, so here I'm just showing a bunch of we can develop and then this kind of mathematical models and for the inference. But how about the large language model, right? So we also kind of tested and then large language model. We have been kind of tracking it, and in the past 4 or 5 years, we're also pretty shocked in their improvement. So I can share with you and some of the findings we have here. What are the pros and the cons? So earlier I talked about you have this Raven's progressive matrix. When we just did this test at that time, and the ChatGPT vision module not show up yet, and then we have to turn and then these types of tasks into and something and a kind of a language input. So the 2022, what we did is that pretty much borrow the similar ideas of the Raven's progressive matrix, but create the digit matrix. And so now, rather than using shapes, because ChatGPT at that time cannot see, but they can read digits here. So the digits will correspond to and then different shapes, but we can capture and the difference and the type of the rules and include it and in the Raven's progressive matrix. So we can use and this progression rules and then your constant rules and the logic problem and so on. We can create and all these different types of combination of the rules to create and then this digit matrix and then ask and then these types of large language model how well they can solve it. So at the beginning when we tried the language model, and they actually were not very good until 2022, and we were shocked. And then actually, and then they kind of the GPT-3 can solve all this problem very well. And then this is the first time we see, and then they surpass and then human performance and across the different types of the problems and so on. So especially for logic problem, it's much better than human. But when we tested, because we invented this new task, and we're pretty confident that and then the system had not been trained by that problem. But now, and probably they know this problem and pretty well. But still give a little bit of hope is that we still have some individual human subjects and then outperform and then the GPT-3 here. So now, so these are the types of the things and we were thinking, and then it seems like it's very impressive, and these types of the system and the start and to show this emergence and the ability to be able to figure out the relations and between these different entities and then just apply it to solve the new problem. So the other things we also did, and then in psychology, besides the Raven's progressive matrix, and then you can introduce these letter string analogies. So that means, and then so we have alphabet, and then we're familiar and then with this sequence. And now we can introduce different transformation types, and then you can have these successor rules, and you can have and then the other types of sorting rules and so on. And you can ask just to show one example, one-shot learning, and then let the GPT and solve the problem. So it turned out it also did very well. If I put the GPT-3 with the UCLA students, and then they are pretty good. And then so at that time I was thinking, and then for all these types of new problems, and they solve it very well. But there are domains we find, and they actually make very interesting mistakes. One of the problems, and we found, is to really do problem solving. So in this particular case, and we use materials and from a developmental study, which is tested and then about young children, and then in the age about 5 and 6 years old. So you can see and that this is the problem. And so in this case, and then what you tell the kids is that now, and then I can read it. And now, so you have the 2 balls and then on the table, and 1, and then you have a lot of gumballs here. So now, and then what you are going to do, you are giving a bunch of the tools, and then to the young children, will say, okay, now I want to move these gumballs and from the left one and to the right one. And you can use any of these tools to solve this problem. Okay? So because the kids are pretty young, and then sometimes they will have trouble of figuring out how to solve this problem. Now, in this case, the next thing in the analogy situation is that now then we can tell them a story. And then this story is given, and then called like basically in the kid's story and the form, and then purely it's a language and a narrative. So now what we can do is that I can tell you a magic staff story. So the story and basically tell the kids that a magic genie and who has moved from his old home and to a new home, and then want to transport all his belongings and like jewels and between and then these homes. To do so, and they create 2 conditions. One condition is that this genie and actually use a magic staff and to pull the other house and then over and to get it closer to the current house, and then they can transfer and the jewelry and by hand. And another group of kids, and then they are giving under the story is that, oh yeah, this genie has a magic carpet, and then they can use this magic. They roll the market like this magic carpet, and put the jewelry and into this magic carpet, and transfer it, fly it through, and to a different house, and so on. So you can tell and this fairy story and to the young children. So you notice that then for this group of children, if they were telling the story about using the magic staff and to pull the house from one place to another place, this group of children is more likely and then to choose and then this basically walking cane, and there was a pull and then this a ball and from the right and to the left, and then move and then all these gum balls and from one to the other. So if you tell them and then this magic carpet the story, they start will choose and the tube, and then they can get to the tube, and then they move and from the gumball and from one to another. So that means is that after listening and this imaginary fairy story, they actually can capture and the basic structures and transfer the knowledge and to solve this particular problem. Now we gave exactly the same material and to GPT-3 because this is the language input, which is great, and we just gave, and then now I'm trying to solve this problem, and now we can give this story, and then ask it, and then to propose the solution here. So I think actually it's very funny, and then to read the solutions from GPT-3. So for example, if you like, it will give you this long, elaborated solution, but if you read it, it's like every step makes sense, but you cannot put them together. So they basically will give you this mechanically nonsensical solutions. If I read it a little bit, they will say, first step, you take the carpet tube and cut it in half, and then place one half of the tube and then in the bowl, and the other half to the empty bowl. Then the third step, and suddenly is take the poster board and cut it into the stripes, and then tape the stripes together to form a long rope. And now, you tie the rope and then to the handle of the walking cane, and then you put it on the table, and you place the walking cane on the table and hold it in place, and then finally somehow magically the gumballs will get transformed. Right? So if I look at every step, it makes sense, but you cannot put them together. It's not a solution. So our take-home message, and then at least in 2023, is that these types of a large language model and somehow started to emerge under the ability to find a solution for some analogy problems. But how they encode the relations, and still it's a mystery to us. But on the other hand, because their training data and still is a language and so on, so they still have the limited ability and in terms of like understanding about the physical world. And if you do the problem solving or analogy problems, it's more relevant than to physical models. And then I think that still is the weakness and for these types of model. So
can one conclude the first part? Can one conclude that LLMs have acquired an emergent ability to solve
some of the analogy problems? So the ones that we use like the like a digit matrix and then or the letter string, these types of the problem, and then you can give them like a one example. They seem to would be able to and then to solve it. But here the question here for us would be like, so what kind of how they solve this problem? Some of the problems can be solved and by in their training data. They have seen it already. But for some of the problem we made for new, so for example, the digit matrix problem, the first time to show up there, I think part of the reason and they're doing well is that they actually have some kind of relation knowledge, kind of like basic rules, successor rules, and all these things. And then they actually can get and then these types of relations, and then they can make use of it. But if you just create some like very new relation, or the relations more related to the physical world, that's like where and then they tend to show and the weakness.
Is that, can one actually, in some sense, do experiments to show that the problems, when it has to solve analogy problems, are invariably or most often or always due to lack of the understanding of physical world, or it could be something else altogether?
Right, so that's kind of like some of the experiments and we're doing, and then to create the new materials, and then to create and this kind of control experiment, or to lesion and some of the layers and to see and their performance and change. And I think Ada also has some work on that.
So just on that, so other experiments, I will show some of them tomorrow, show that they're just terrible at sequential tasks of any kind. So sequential reasoning, the more steps you have, the more it starts to hallucinate and say nonsensical things.
Yeah.
And so some of the issues are basic reasoning issues and not just a matter of analogy. And some other issues are maybe related to the physical world. However, because it has this kind of a semantic association and vector-based understanding of the relational structure of the physical world, I'm guessing a lot of it will have to do with the reasoning issues. I think it would be interesting to decompose the reasoning versus physical sources of failure.
Yeah.
And that's a very easy experiment we could do within this 3 months, actually.
Yes. Yeah.
To what extent do you think that the physical understanding of the world is crucial for this type of task? For example, when 4 to 6-year-old children say that use the magic stick to bring something close, I've never used a magic stick before that. Like I know what a cane is, what function, what is the purpose of its function, and where it's typically applied. But as humans, even children that young can extrapolate or generalize to this kind of novel scenario without having interacted with that object before.
Right.
So, to what extent do you think that physical understanding of the world helps with this?
Yeah, I do think it's quite important, and then because if you, I think young children and compared to the large language model is that they still get lots of the time and then kind of opportunity to interact with the world. And then because they have a body, they can move around, and then they can play, they can sense about the force, and then all these things is missing. And then in the large language model, because it's on language description and still at a quite abstract level, you are going to miss and all this sensory information here. So for the young children, probably they never play and then the walking cane, but they play the other toys. And then so they kind of like get the sense about the basic kind of physical mechanisms. So that's kind of like in their repertoire, and so they can apply it. And then you use them in this particular situation. I do think and then this physical the interaction with the physical world, with the social world, is very important.
So try to dig into what your answer now. There are two maybe different things. One is the physical world, and the other is interaction.
Yes.
Because we can also think of so these models are trained for the most part on non-interactively. I mean,
Right.
they don't get to play and explore and ask questions.
Yeah.
So can we again disambiguate? I mean, I think I completely agree with the comments there that it's important to disambiguate there because either is the issue with reasoning or the physical world,
Right.
but also we can ask, is the issue interaction or the physical world?
Yes.
And I'm curious also what you
Yeah.
think here, because to me these are two very different things.
Yes. So that's actually why it's interesting and to using this analogical task, because you can create the problem of very, very different natures. You can create the problem you are trying to solve had nothing to do with the physical world, kind of a letter string, pure and rule-based and the Raven's progressive matrix, these types of things. That's kind of like can target on more reasoning aspect. But now you are trying to solve a specific problem, you can create the problem that's needed the physical knowledge or that's needed the interactions. And then just to see and then where they're going to end up break. And in this particular case, so my thinking is like you can create another problem that maybe they can share the same types of the rule structures, but they need a different domain knowledge.
You think the issue is the interaction or the issue is the physicality?
I think it's both because through interaction, we learn the physical world. Yeah.
I mean, you can learn, you can have physical, you can observe the physical world without
Yes,
interacting, and you can interact in the, just through text and digital space.
Right, and then but in a lot of situations, and then these types of pure observation. So that's kind of like interesting things, and we can discuss about it. It's like the pure observation. You may need a lot of like the data, and then across a very large and diversity, and to learn and then this kind of physical and principles. But if you are able to interact, and then you probably just need a way less amount of the data, and to be able to learn and then to abstract out this physical kind of like properties and mechanisms and so on. So I think it's like I kind of think that the interactions it become like one of like very efficient learning approach, and to be able to learn under the physical world and better. Yeah, but But I think the ideal situation here is that for humans, and then we don't only have language. We have all these different senses, and then all these perceptions, and then the audio, and so on, and then the touching, and then all these different senses. And they actually gave the representations about the physical world, and then we can align them and to get the better representation about this physical knowledge. So I think that actually integration is important. That's what kind of interaction can help us. And the other things I also think the interaction is important is that it's related to this generative model for relations, because if we can interact with the world, we can intervene. And then for the complicated system, and we can change the status of this system, and we can observe what's going on there. So we can create like better training data for us. Oh, Mark?
So, I mean, I find myself, if I'm trying to solve this problem, I'm running a little movie in my head. I'm imagining the process of doing it before I would start. And I have a feeling, again, that's what humans would tend to do. And, that probably is testable, right? I mean, we have lots of MRIs on this campus that could give some evidence of, in the first set of problems, whether in fact people are using their language skills or not to solve it, whether they're using these ability to visualize a sequence of events. Of course, then that might suggest, would it help if something like ChatGPT saw a lot of videos of some of these physical solutions, whether that would be a substitute for, since they don't have to actually physically do it, whether that would be a substitute. Because I don't think people would use language to solve this problem.
Right. Yeah. I think that will be very interesting to see. And then when you have this kind of extract the knowledge from the language, and now you also have this kind of like imaginary sensory input, how you integrate them together.
It might be challenging to relate this to MRI or fMRI studies, because the link between the two are tricky between the performance and this, because of the activation timescales and
Yeah.
length scales in MRI are very different than the timescale over which one solves the problem.
Right. I think a behavior test probably will be easier.
Yeah.
And then they directly look into the brain. And then, but the behavior test and then can be the first step. And then to create the situation. Another thing, I think these types of the models also gave a incredible tool here, because now you only have the language inputs and you really can test and what's the boundary of the knowledge representation there. Heather?
There are folks at MIT, I don't agree with them.
I know that, yeah, I agree with that.
Exactly.
I think
So-
just not,
Yeah. Something I wanted to say to the question in the front. So there has been solutions to games that is very difficult for agents that with regular deep learning architectures to solve. They had them watch a lot of YouTube videos of, let's say, Montezuma's Revenge played by other people, and then they could kind of find solutions based on that. So that approach is used. However, it does not work very well with regards to visual sort of VLMs, like visual models right now. It's not trivial, and also sometimes they have difficulty generalizing. So we trained models of 220 million parameters and 1 billion parameters on a large amount of video based on the gameplay. It turns out when you look at how they behave in the game, they are not acting in a way that you would assume they have learned it. So it's very not trivial. There is some solutions that work, some that don't work. It's a very complicated thing. But using videos to train has been used, especially in the context of games.
Okay, I think you tell me and I need to stop. Okay, so we can discuss after this. So I think should I stop now? Right? Yeah. Okay. I think it's 12 and then it's basically the lunchtime, and then I will stay here and then I'm happy and then to discuss and with people. Okay. Thank you.